was special. Okay. Okay, we are now recording. Let me make again the announcement about the math team. Did you decide you probably can't do it, or you?
I probably can't do it.
Okay, all right. I think she said she may have enough, but I wanted to wait till Jasmine gets back to see if she wants. There she is. Did you want to try to do math team practice today or not? You can? 3:15? Okay. Okay. And till about 4:45, you said? Okay. All right, we can stop anytime you need us to. Okay. Now, are you pre-engineering or math or what?
No,
Pre-engineering. At some point, you'll probably be taking, they used to call it the EIT, Engineering and Training Exam. There's something else they call it now. Is that, do they still call it?
Yeah, they call it the FE exam. Or that's what you're talking about? Or you...
Now, I know there's PE exam later.
Yeah, that's later.
And what's this one called?
This one's called fundamental exam.
Oh, okay. Maybe that's what it is now.
It's pretty much the same thing. It's
Okay.
EIT.
Yeah.
EIT exam.
Yeah, and what happens with that, at least one section is mostly math.
Yeah.
So if you are going to be taking that anytime soon, even if you're not going to participate in the math team, this might be great practice for that too. But you don't have to. I'm just saying it's available. We're going to be doing it anyway. So
Yeah.
Okay. So it may be just you and me here today, but we'll, if we know of anyone else, we'll do it. You want to do every Monday, Wednesday, or what? Okay. Well, then we'll try it then. And I don't have the questions yet, so I have to get those. I think Dr. Thomas said she had them, but I think we can get them online too, and we'll try that if nothing else works. Now, because of that, your physics class will probably move next door because he's going to already be teaching a class in there, and he'll just stay in there. Okay. Are you in physics also?
No, I'm
Okay.
not.
Okay. All righty. Well, enough of that done. Now, where we left off last time was on chapter 12, vector geometry, section 12.6, the survey of quadric surfaces. And this is where your first test actually begins. Everything else is the background you need to do this and what's coming next. But this is where the test begins. So let's start the slideshow from the current slide. And we did this slide last time. This was the and I was telling Treddy this morning in my Cal 2 class, PowerPoint just went crazy. I was riding along somewhere, and all of a sudden, it shut down Blackboard. And then when I was waiting for it to come back up, it was in the process of coming back up. And I was talking about, I hope it doesn't lose it. Then it just decided to shut down the whole computer, and then started doing updates, upgrades, Microsoft upgrades. Just right in the middle of class, no warning at all. So hopefully that won't happen again. I've never had that happen in Windows 7, but it did it. Okay. This is the hyperboloid of one sheet, hyperboloid of two sheets, and remember how you tell the difference of these analytically is this would be x over a squared plus y over b squared. And then the way I like to write it is minus z over c squared is equal to 1. That's how this would look. Okay? How that one would look would be, now they oriented that slightly differently. X over a squared plus y over b squared, and you don't see the a and b's on this, minus z over c squared is equal to minus 1. Okay, now they wrote it as plus z over c squared minus 1, but that's equal to minus 1. In other words, you'll never have anything. 0, 0, 0 will never be on that. Okay. So, anyway, we had already done that. We were ready to do example 2. And that was this part. Okay. Just barely be able to fit this on a slide on one screen here, but let's try. Okay. Traces of the hyperboloid of one sheet. Determine the traces of the hyperboloid, and this is it, x over 2 squared plus y over 3 squared is equal to z over 4 squared plus 1. Okay? Now, that's one way to write it. That's how the book writes it. I like to write it, put a minus z over 4 squared here is equal to 1. That looks more like your circle and your ellipse. It's just that you have the minus sign there. And that also enables you to look at the traces more easily, I think, anyway. Okay. So here's how we do our traces for this one. Okay, first, let's take z equals 0. Okay, z equals 0, what does this produce? X over 2 squared plus y over 3 squared is equal to 1. That's an ellipse, exactly. Minor axis on the x-axis plus and minus 2, and major axis on the y-axis plus and minus 3. Okay, so there's your ellipse right there. There's a trace where z is equal to 0. And then if you start increasing the z's, okay, you just get bigger and bigger ellipses as you go up or go down. Because as z gets either increases or decreases, this gets to be the number you're adding to 1, so it's bigger and bigger and bigger as it goes down. So there's your traces, horizontal traces. Okay. Your vertical traces, I would start with this one, that y equals 0. That's going to be in the xz plane now. And that would be, again, and this will now be, if you move this over here, which to me makes more sense, minus this, that would be an hyperbola with x-intercepts at plus and minus 2, and you can't really tell a lot from that plus or minus 4 except just not a lot you can tell about it. But that's these pink looking hyperbolas there. There's the one on this side and the one on that side. Okay? And then do the same thing. Say x equals this. Oh yeah. And then for any y's plus or minus from 0, then you start getting these pink traces. You still get hyperbolas as your y's are coming here. You see you've got the faint colored pinks on the back side and the same here. So you get more hyperbolas where y is plus or minus anywhere from there. Okay? Now, say x equals to 0, and you subtract this over here, and you get a hyperbola, y over 3 squared minus z over 4 squared is equal to 1. And there's your green one here, plus 3 and minus 3. Okay? That's when x is equal to 0, was it? Yeah, x is equal to 0. That's that hyperbola. And then as you let x get greater or less, now, I haven't done a really good job on illustrating this one to it. You see some of these as you come out on x, then you have here's one and there's one. Besides this one that we had at the beginning here, which is hard to see here. I think that's it right here. It's real hard to see because they have them so dull. And, one on the back side there. But then you have hyperbolas as you come out this way or as you go back that way. Okay? And these, I'm sorry, I looked at the wrong there's a y is equal to plus 3. And I can't see y is equal to negative 3. It's somewhere right back there. It's that one there, but it's dotted. You can't see it when you draw the others out. And then as you do others coming out, they don't show as many green ones as they did the red ones, but you would have more of them in there. There's one, there's one. On the back side, you've got them too. In fact, that's the one that we see here. That's the next one over that you would get there as you are moving. Yeah.
I see that's what you mean by line, but what did this line come from?
That I was just looking at that.
This line right here. What
Oh, that one. Okay. That's also hyperbola here, and that's what I was looking at too, saying, how do they get that one? Okay, and that would be.
Does it have to do? Do you have to rearrange the equation to get that?
Well, here's what's happening on that one, I think. Let me make sure. See, there is a point, and you got it with the greens and the red. There is a point where you actually have two lines that go like that. Now, what would that be? I think it's where, let's just take z is equal to 0. Okay? And I want to say where z is equal to 1, but it doesn't seem like either one of those would be at z is equal to 1. They look like it's where z is equal to 0. And you basically have x squared plus, yeah, when that's equal to 0, you have, this is an ellipse. Okay. Okay. But here's what it is. Z is equal to 0, but also y is equal to 0 because it's crossing the x-axis.
Oh.
So with x is out. What you have now is x over 2 squared is equal to 1. Okay, take the square root of both of those. X over 2 is equal to plus or minus 1. In other words, x is equal to plus or minus 2. So when x is equal to plus 2 or minus 2, then you have two lines that cross like this, both of them with slopes of 1/2. Okay? Same thing here. When x is 0 and z is 0, you have y over 3 is equal to plus or minus 1, so y is equal to plus or minus 3. And that's what you have this one and that one. That's when it's minus 3x.
And then same thing for the z one.
Second?
It's going to be the same thing for z one. It's like x and y was 0.
Yeah, okay. So what you have here then is your, what this one is then, is where you, this one's where x, y and z were equal to 0, and you let x be something, plus or minus 2. Now let it's not y is equal to 0, but this thing minus that thing, I'm sorry, where y is less than z. Okay? So if you had pulled this over here, y minus 3 was less than z over, y over 3 is less than z over 4. That would give you a parabola. That would be it. Yeah. Okay. So I think that's the other one. That's where that comes from. And Victor's here. Good to see. Okay, now we haven't seen Sylvester B. McGrew since the beginning. I don't know if he's going to stay in the course or not, but we don't know. Okay, so but the three that have been coming are here, so that's good to see. But that's how you do your traces. Start with the simplest ones on the coordinate axes, okay, and then let the axis, let things increase or decrease one way or another, and you get ellipses going this way, hyperbolas like this, which you'll continue getting, and hyperbolas like this, which you'll continue getting, and then after a while you'll reach these crosses here, which comes when both of these are zero, both of those are zero, and then you have straight lines. And then you get your hyperbolas going like that, and that's where z is greater than, 0 over 4 is greater than y over 3, and you get your hyperbolas coming out x that way. So it's sort of a strange bag, but that's why it's called a hyperbolic, hyperboloid. I can't get my accent right, so hyperboloid, and this will be of one sheet because you do have, this is a +1. That's a -1, it's 2 sheets. Yeah. Okay. And that's how you draw your traces. Okay. Here then is 2 sheets. So I sort of was thinking ahead. I forgot they had one like this. Now a couple of little differences here. That one, your axis of the thing was z, the one that's over there. I like to think the one that's the negative sign. This has y over here, or if you moved it over here, it would be the negative sign. So this is going to be symmetric about the y-axis, not the z-axis like the one before. And again, if you had y is equal to 0, you never have y is equal to 0, because this is positive, that's positive, never equal 1. And that's why y is equal to 0 has no value. In fact, up until you get to y equal to b, then this becomes a 0, and you have the points right there. Anything y greater than b, then you have a positive number here. That gives you ellipses for any of y greater than b. And that's why you get these ellipses here going back negative and going positive, the blue ellipses there, for b on that. Okay? Now, cutting any other way, let's take z is equal to 0. And again, y has to be greater than b. Okay, greater than or equal to b, or else you get nothing. Oh, that's always positive. If y was less than b, that would give you something negative. So y has to be greater than or equal to b. If it's equal to b, again, you get that point there and that point there, and that's all. Anything greater than b, with z equals 0, then you get, real hard to see, those would be the green hyperbolas like this. I'm pretty sure. It's just so hard to see in here. The green hyperbola is like that. And where x is equal to 0 and y is greater than or equal to b, you get your
I see the y.
Yeah. I'm looking for the z's here. X is equal to 0, that would be here. Then that would be this pink curve right here that goes through minus b, and there's also one here that goes through positive b. And that would be in the yz plane. Those are the hyperbolas that way, and then you come this way, or go back that way in x's, and you get more hyperbolas there. So it's a hyperboloid, 2 sheets, because of that -1. So your traces parallel to the XZ planes are going to be ellipses once you get past y greater than or equal to b. Your traces in the XY plane are going to be these green ones like that, okay? And the traces in the YZ plane, once you get y greater than b, those the YZ plane, those are your peak ellipses like that. Okay. I mean, hyperbolic like that. Yeah. Okay. Now, we have a shape called an elliptic cone. Now, what's the difference here? Now, before I write any further, let me go back. I'm not sure, Victor, if you were, I don't think you were here when we did it. Let me write a few of the standard shapes for you. Well, okay. And I think it's a good review for all of us. A circle be x over r squared plus y over r squared is equal to 1. Okay? We're used to seeing this x squared plus y squared is equal to r squared. But written in the way we're going to do it here, that would be a circle. To make a sphere, it would be x over r squared plus y over r squared plus z over r squared is equal to 1. That would be x squared plus y squared plus z squared is equal to r squared. That would be a sphere. Now, to make this an ellipse, x over a squared plus y over b squared is equal to 1. That's an ellipse. Now, you can change the x to z or the y to z. You do it in any plane that you want to, but that would be it. An ellipsoid is x over a squared plus y over b squared plus z over c squared is equal to 1. Okay? Now, if two of those axes were the same, then they'd have the same letters on the bottom. But if all three are the same, that's your circle. I mean, your sphere. Okay? Now, that's an ellipse. Here is a hyperbola in 2 dimensions. X over a squared minus y over b squared is equal to 1. Okay? And you could change x and y or y and z for y, whatever. But that would be your hyperbola in a plane. Now, to make it a hyperboloid of one sheet, it's x over a squared plus y over b squared plus minus. And this is why I like to write it with this way. The book likes to do it the other way, but I prefer this way. Minus z over c squared is equal to 1. That's a hyperboloid of one sheet. Hyperboloid of one sheet with z as the axis. If you want to change the axis, just swap any of these around. Make this the y, z, x, or z, x, y, or x, any way you want to do it, just swap them around. Whichever has the minus sign, that's going to be the axis. Okay? That's the one sheet. To make it of 2 sheets, then we do x over a squared plus y over b squared minus z over c squared. That makes a hyperboloid. 2 sheets make that a minus 1. Okay, now it 0, 0, 0. You will not be at the origin anywhere close to the origin because it just isn't going to work. Okay? And again, this z will be your axis here. Flip the letters around, then you have your axis going anywhere. Okay. Now, let's move to the elliptic cone. Now, they write it this way, but I write it this way. It looks so similar to this one, x over a squared plus y over b squared minus z over c squared, but this time it's equal to 0, not plus 1 or minus 1. That makes it a cone. Okay? Now, let's picture this. When this equal to positive 1, you get one sheet. If it went to 0, then this part and this part, it's just your waistline is getting smaller and smaller and smaller until it goes to 0. Then you have a cone above and a cone below. And that's equal to 0. Then when it's minus 1, they actually separate and start going like that. So that, to me, makes more sense than the way, the way they do it is fine. But this, then, is your elliptic cone. You see, put this over here and it's equal to 0. Now, the point 0, 0, 0 is on that. And if you think about it, it's the first time the point 0, 0, 0 has been on any of our shapes. Okay? Any of them. Okay? But now it is. And that's the only point there. Anything above, and that's when z is equal to 0, you have the point x equals 0, y is equal to 0. If you pick z any other point, positive or negative, then this is some positive number squared. So now your ellipses with that, as a number there. That the ellipse going up and the ellipse going down. Okay? That's why they call it an elliptic cone. Because it comes to a point at 0, 0, 0, and it's ellipses everywhere else. Now, if you wrote it like this, so y equals 0, here you have an hyperbola. Okay? As x equals 0, there you have a hyperbola. And you'll see, yes. No, you won't.
Yeah, I was about to say, I don't think you're going to have it.
No, okay, yeah. Let's show what you'll have. They are hyperbole, but if this is equal to 0, then this comes over here, and you see these are hyperbole going this way, because this is okay. With that equals 0, I'm sorry, you're right. I said it wrong. Let's go back to my question. Okay. I said it wrong. I meant for, with this being 0, what you have here is move that to the other side, and you have x over a is equal to y over c, plus or z over c, plus or minus, right? And that would be the slope like this, and then with x equals 0, you have y over b is equal to z over c, which would be two lines that intersect 0. And that's exactly what you've got here when they intersect. You got this. Okay. There it is. There's the one that goes to the origin here, and there's the other one that goes to the origin. Those are the pink ones. The green ones, there's the one, and there's the other. It's really hard to see. They're right on the edge of the thing. Those are the two lines like this. Okay? That's when it's equal to 0. Now, when this is equal to any constant, let's just say b, okay, then this will be 1, okay, and then you'd have z minus c minus x over a squared, if both of them are squared, is equal to 1, and that would be ellipses in the parallel. This is y is coming out, going back. These are your hyperbole like this, and you got them over here too. And then when x is equal to a constant, then you have these green hyperbole like this, and the ones on the back side too. So in x and z, y and z. So you have the hyperbole that way too. But when it's equal to 0, that makes your straight lines. Okay, now, I'm sorry, I probably should have blown that up. It would be a little easier to see, perhaps. Okay, now I can write that as minus c equals 0. And there's at least part of that green line. You can't see the other part. There's the tip of it there. And then the red line here that goes through like that, and that's the one that goes through here. You can't see the backside of it. It's right there. That's a faint line like that. And those are when y is equal to 0 and x equals 0. Those cross lines. Now, how about if z is equal to 0? That gives you the point 0, 0, 0. All you got there. Okay. And then come out with x being constant. You're coming out with the green hyperbole here, and with y is equal to constant, you're coming out with the red hyperbole. Okay. There's your elliptic cone. They don't do any problems with that, but now we get to paraboloids. Okay? Now, before I do this, let me go back to this. Okay? There was a circle and an ellipse hyperbola. Let's do a parabola now. Parabola is basically this. Y is equal to x squared plus 1. We'll just say plus 1. That is a parabola, right? And it's for plus or minus x's, you get the same y, right? So that's hyperbola. A parabola. I keep saying parabola, okay? So what would it mean for a paraboloid? Okay? Now, there's several different ways you can express it. But the first way, I'm going to sort of think of that y as a z now. And I'm going to say x over a squared plus y over b squared is equal to z. Not z over c or anything else, just z. If it was over c multiplied by 1, mess with it, but that's it, okay? That is a paraboloid where when z is 0, you have ellipses. So you call that elliptic parabola. And z is any constant that gets bigger, like that. Okay? That would be an elliptic parabola. Okay? Anything else where x is equal to 0, you have a parabola in z and y. And when y is equal to 0, you have a parabola in a and b. So let's go over here and show that. Okay? Okay, now they put their z out front. I put it on the other side. It doesn't matter where you put it. So in other words, this is an elliptic paraboloid. Z is equal to 0 or any constant, and you have a series of ellipses. Okay? Let's say y is equal to 0. You have a series of parabolae with, back up a moment. Z is equal to 0. You have one ellipse on the xy plane, right? X, major or minor x is x equal plus or minus a, y is equal plus or minus b. Just an ellipse there. Now, here's the thing to note. This is always positive. This is always positive. You add them together. Positive numbers. So z can never be negative. So you just have it opening up here, and that's why when you go y is equal to 0, here you just have a parabola. Because you don't have anything down here. Just a parabola this way, parabola this way. You come out here or out there, you just have parabolas like that. So that is an elliptic parabola. Elliptic paraboloid. Ellipses here, and the ellipses get bigger and smaller as you go. And this is what it looks like. Right here. This is your elliptic parabola, because your blue traces are z's equal various numbers, and then when x equals 0 or constant, you get your pink traces like this, and when x equal constant, you get your green traces like this, y is equal to constant, you get the pink traces like that. Okay? That's your elliptic paraboloid. should have blown that up. Sorry, I forgot. Okay. Elliptic parabola. The blue curves in there are ellipses, and the green curves along x equal constant, those are parabolas, and the pink curves, y is equal to constant, plus or minus, those are parabolas. Parabolas going that way. That's how the elliptic parabola looks. So you equals 0, or any constant, and you have ellipses, and this equals 0 or any constant, you have parabolas in the xz plane, and this way this equals 0, you have it in the yz plane, or parallel to the yz plane. Now, what if that were a minus sign? Obviously, that's not purple, right? So it's a hyperbolic paraboloid, because the z is only to the first power. Or you can rearrange any of the variables you want to, but this will be the axis here. It's harder to talk about an axis there, but let's take a look at it now and see what happens. Okay? Now, if y is equal to 0, you have a parabola in the xz plane. And there it is. Y is equal to 0, it would be that parabola right there. And y is equal to any constant, it would be these parabolas here. Okay? Now, if they're opening up, because this is parabola with a positive a here, you know it's going to be opening up. But if x is 0, this is a parabola going down, and this is your green curve like this. Okay? X equals 0. And then x equal any other constant, and they're doing like this, but these always are concave down. Okay? So you have parabola going that way. Okay? So when z is equal to 0, you have just one, you have, again, a set of lines, x plus y is equal to 0. Let me see if I can find that for you. It's this line right here, that's the blue line for it, and the pink line, no, the green line, there it is. I think that's part of it there going there. I do not see it. They don't show a view of it well enough to see where that crosses. But I think you can see the pink. Now there's blue. They're both blue, that's what. Right? Yeah, they are. That's one coming in going this way, and that's one going that way. Because that would be, when z is equal to 0, you're in the xy plane, and in the xy plane you only have that, and parallel to the xy plane is your, that's these blue curves here. Okay, really hard to see here. There's a blue here and a blue there. Okay. It's a rare, and from this angle it's hard to see. Okay. So if we go back to this one, we're writing them all, then this would be x over a squared minus y over b squared is equal to z. Okay. So when z is 0, you have two lines across, and z is any other constant, you have hyperbole in xy plane. Okay? When y is equal to 0, you have a upward curving parabola, xz plane, and when x is, or any constant, and when you have x equal 0 or any constant, you have downward. That's what makes this shape here. Now, Another thing to call this is a saddle. You can picture your horse being along the x-axis and your legs are going this way. So it sort of looks like a saddle. And you actually call that point in there a saddle point. You'll do this later where you have a minimum in this curve and a maximum on that curve. That's the saddle point. Okay. You'll run into that later. So just for the fun of it there. Rearrange your variables any way you want to, and you've got it going in different directions. The horse may be along the x-axis and your legs along the z-axis or something like that. So you just rearrange that if you want. Now, there was a thing we skipped here, and let's show this. I think it's what we've already talked about those axes, I think. Okay. Not quite. Your elliptic paraboloid, your horizontal traces are ellipses. We talked about that. And your vertical traces are upward parabolas, whichever way you go. Okay. Your hyperbolic parabola, your horizontal trace, is a parabola, and your vertical traces, either on x or y, on one of them will be upward parabolas, and on the other one downward parabolas. We mentioned that on both of them. I was either dropping coins or something. I heard something hit the floor. Okay. Now, they said they weren't going to do this, and then they turned around and did it. Okay? But just for your, I guess, cultural enlightenment, okay, what they did, they twisted it. Okay? Where you're not along the x or the y axis, but you're along x minus y this way and x plus y that way. X minus y equals 0, x plus y equals 0. That's where the horse goes on this one, and your legs go over that one. If you were to write this out, this is how it looks. Okay, let me blow this up. I keep forgetting to do that. They said they weren't going to do it. Remember, at the very beginning, they said they weren't going to have any cross terms. Sure enough, they did. Okay. But if you have a change of variable, okay, then you have z is equal to this, so you have the new axis u and v, and that becomes your axis. And that's how you adjust for the cross term here. Now that works only when it's exactly xy. You know, if it was xy over 2, then you have to twist it a little differently. We're not going there, okay? They said they weren't going to go there, and yet they did go there. Okay.
I don't understand that.
What's that?
I said good. I don't understand that.
Yeah, they said they weren't going to do this to you, but they wound up doing it. One way you could look at this is, I'm not sure this is helpful, you can factor this and say z is equal to x plus y times x minus y. So there's your x plus y and there's your x minus y. Then that becomes the axis of your v. It's just a 45-degree shift. Z stays constant. Okay. Like I said, they promised they weren't going to do that, and then they did it. Alternative form of a hyperbolic paraboloid. And that's what example 4 was. And actually, I didn't quite if they started off giving you that, z equals 4xy, okay, then you have a change of variables of u equal x plus y and v is equal to x minus y, okay. Okay, what they say here, show that z is equal to 4 plus y. I'm going to take this. Show that this, okay, is a hyperbolic paraboloid by writing the equation in terms of two new variables, u is equal to x plus y, that's a u, and v is equal to x minus y. Okay? Now, here's what they note, that u plus v is equal to x plus y plus x minus y, which is equal to 2x. In other words, x is equal to u plus v over 2. Right? Okay? Let's do the same, but this time let's do u minus y. No, u minus v. That isn't right at all. U minus v, and that would be x plus y minus x minus y, and that would be x plus y minus x plus y, and that would be the x's go out to y, so therefore y is equal to u minus v over 2. Okay? So let's go back to our original thing. Z is equal to 4, x is u plus v over 2, times y is u minus v over 2. Okay? Well, 2 times 2 is 4. The 4's go out, and then you have this is equal to u plus v times u minus v, which gives you u squared minus v squared. Okay? And that's how you get it. That's all they wanted you to do with this, to show that's true. What you do is you have a change of axis, is all you do. Okay? And basically, it's a 45-degree twist. Don't think you'll see many like that again. Okay. All right. That was just example 4. It says, show that we just did. Okay. Now, this is yet another fairly new concept. Okay. If I said, draw me a cylinder, okay, I doubt if any of you come up with anything that looked like that, would you? If I said, draw me a cylinder, most of you say, oh, that's a tin can. Right? That's what we think of as a cylinder. And that is indeed a cylinder. But what a cylinder is a geometric shape in one axis, like the XY axis, extended infinitely in the Z direction. This shape has to be a circle extended. So that's a right circular cylinder. That's your tin can. If that had been an ellipse, then that would be a right elliptical cylinder. If it had been hyperbola, it would have been a right hyperbolic cylinder, and it would have just gone like this. This is a cylinder of some curve. It looks like that could be a sine curve that's been had a constant added to it. Y. Let's see. If that was plus or minus 1 at the equilibrium point, say plus 2. Okay, so this would be plus 1 here and plus 3 there. That could be the sine. Y is equal to sine x plus 3, or something like that. That would be a cosine x. So it starts at plus 1. Cosine x plus 3. So that would be the curve on the xy plane, then extend it infinitely. It doesn't have to be closed. That's a closed curve. This is an open curve. It's a cylinder. It's just not a closed cylinder. Okay? Just like that's a closed curve. A circle is a closed curve. A sine wave is not a closed curve. It's an open curve. So that would be your cylinder with base C, whatever that curve is at C. And those would be quadratic cylinders. Yeah.
Just to make sure something. So you said that it would be cosine x plus 3?
That's what I said.
Okay. So if you switch it the other way on the y-axis, would it be sine of y.
Cosine of y plus 3 or something like
They
that.
still be same.
Well, I don't know what you mean by twisting. What I was doing was looking at this curve here.
Yeah.
Okay. It looks like x equal cosine y, because when y is 0, x would be. No, I'm sorry, I said that wrong. Y is equal cosine. Did I say it backwards? Is that what you were getting at? Y is equal cosine x would be this curve here, except do cosine x plus 3.
Okay.
Because cosine x would be your y value 1, and then add 3 to it, and you get it up here. So it goes down as low as 1 and up as much as, make it plus 2. Okay. Y is equal cosine x plus 2. So this becomes a plus 1, that goes to a plus 3. Okay. I think I said it backwards. I was trying to make it a sine, then I changed the cosine, but I didn't adjust it. That would be this curve here on the xy plane, the y is equal to cosine x plus 2. And that would mean your minus 1 goes up to plus 1, your plus 1 goes up to plus 3. And your equilibrium would be at 2. X equal 2. At y equal 2. That would be your, that may not be the curve. I was just picking one that looked like it sort of looked like that. Okay. And then the cylinder would just let z equal whatever. So if it's a three-dimensional graph, the equation looks just the same because you don't have any z dependence there. Z can be anything. Okay. They do have another term in here. I guess I'll just say it because they've got it here. Ellipsoids, hyperboloids, paraboloids, quadric cylinders are called non-degenerate quadric surfaces because they all have a surface. Okay? But remember that if we said x squared plus y squared plus z squared is equal to r squared, that would be a sphere of radius r, right? But what if that r was 0? It's a point. That's 0, 0, 0. That's all you got. That's degenerate. It collapses to be a single point or something else, just has no shape at all, no surface to it. So a non-degenerate quadric surface has some sort of surface to it. A degenerate one collapses to a single point. Don't need to know that very much. Okay, let's take a look at this and you tell me what we have here. Oh, okay. All right. What would that be? Right, a circular cylinder. It looks like a circle at the bottom. This would be a? What's that? You can read it over my hand. Huh?
Yeah.
All right, elliptic cylinder. See that? And this one would be hyperbolic cylinder. Notice it's not a closed curve because a hyperbola is not a closed curve. Hyperbolic cylinder. I mentioned those earlier. Let's do the last one here. That would be a parabolic cylinder. The base curve is just a parabola, and you just extend the z. And guess what? Oh, yuck. Okay. Let's go back so you can read them again. All right. If this is all you had, what would you call that?
Sorry, say again.
Just the equation.
It'll just be a regular cylinder. Or
If that equation, I gave you that equation, what would you call it? If that's all you had, just that equation, I would call that a circle of radius r.
yeah.
But if you're in 3 space and have that, then it makes it a cylinder. That says there is no z dependence. Z can be anything in the world. So the equation looks just like that of the base, the circle, but if you're in 3 space, that means the z can be anything. That's what makes it a cylinder, right circular cylinder. Okay? Same thing here. If that's all I gave you, or the book gave you, I would be tempted to call that an ellipse. It would be in 2 space. But if you're in three space, that means the z can extend anywhere.
Oh,
So
okay.
that extends up, and that makes it a cylinder. Same thing here. If that's all you had, I would be tempted to say that's hyperbole in a plane. But if you know we're in three space, that means z can be anything. That makes it a cylinder. The same formula, but if you're in three space and there's no z mentioned, then it can be infinite in either direction. Whatever shape you have, it just extends it. And that's then same thing here. If this is what you were given, that's just a parabola. If you're in two space, but if you know you're in three space, that makes it a parabolic cylinder. It can go up and down and z infinitely, either direction. That's what makes it a parabolic cylinder. And circles and ellipses are closed. Hyperbola, parabola, and most other curves are usually open. All right. This is in the summary. Let's do these to begin with. Okay. What would that be? Oh boy, it's out there too. It's an ellipsoid. Oh, I didn't do this well. Let me go back. Do this again. I didn't know the titles were on top. Wasn't paying attention. Okay, this one. This is an ellipsoid because the traces in any plane are going to trace out ellipses until you exceed the boundaries of it. X has to be less than A, Y has to be less than B, and Z less than C. That's going to make your ellipse. Ellipses, any trace there would be an ellipse. Okay? Put them all together, that's an ellipsoid. Okay? And again, they like to move the Z's back and forth. I like to keep on the same side. Make that a minus Z over Z squared. That would be an elliptic hyperboloid, okay, of one sheet because it's a plus one. And I would go and stick the cone in here and say it's an elliptic cone, okay, and the elliptic cone would then be with the zero here, okay. Notice I'm leaving that with zero. And then if you make it a minus one, then you separate that cone and you have a hyperboloid of two sheets, and that's with the minus one. Move this over here. All three of those look identical except the plus one here, zero for the cone, and minus one for that. Okay? To me, that makes a little more sense. Okay? Not that I'm griping about the book. I guess that's sort of standard. Okay, and there's that cone where you have that equal to zero. Move that over. Let's go back here. This is a elliptic paraboloid. Okay? Parabola because one of these is to the first power, the other is to the second power. Any constant along Z, and you have ellipses, any constant along X or Y, and you have parabola. Okay? With a plus there. With the minus side, that makes a hyperbolic paraboloid because again, so that's your hyperbolic paraboloid. And again, your when Z is equal to 0, you have two lines that cross, the blue lines. When Z is any value positive or negative, if Z is positive, then your hyperbole are the blue lines that way. If it's negative, your blue lines are that way. Okay, we call them below the x-axis. You're along the z-axis. Okay, and if you y equal to a constant, then you have parabolae that open up, and that would be these pink ones here. And if your x is some constant, you have your parabolae that open down. That's the green ones going up or down. Okay, we've already sort of done that. I would call it, elliptic cone. All right, any questions on those? Okay. And then here we have cylinders. That looks okay. That looks like an equation for an ellipse, but if you're in free space, that means that you can go infinitely higher ways. So you start with your ellipse, where this is plus A minus A, here's plus B minus B, wherever that one is right there, and then you extend that infinitely in Z. Okay? Hyperbolic cylinder, it did show a circular cylinder. Hyperbolic cylinder, this looks like a parabola in XY plane, but if it's in free space and Z is allowed, any value for Z takes on, just extends this up or down. Parabolic cylinder, that's a parabola in XY space, but then if you're in free space, we can take on any value, just positive. The same parabola, just trace it up or down. Those are all cylinders. Or any other curve could be a cylinder. It doesn't have to be one of these regular curves. Okay. Now, let's look. Do you find the preliminary questions useful? Oh, that's right. Find them useful? Okay. True or false? All traces of an ellipsoid are ellipses. True. What was that?
Because I'm not sure.
Yeah, that's what it sounded like, unsure. Okay. Let's go back and see an ellipsoid. There's an ellipsoid. All of its traces are ellipses. Whichever axis you trace over, you get ellipses. So yes, that's a true. Let's make sure the back of the book has it right. You know, they could be cheating on us here and mess up somewhere. This is, goodness gracious. Well. Here we go. 12.5 preliminary questions. No, 12.6 preliminary questions. True. Mostly. Except that x equal plus or minus a, x equal plus or minus b, x equal plus or minus c. Because there you're at single points. Okay? So that is the only exception. Right. Well, actually, anything greater than a or less than minus a, you don't have anything. So I'd say all the traces are. They meant it to be. Okay, number 2, true or false again. All traces of a hyperboloid are hyperboles. Let's see. Hyperboloid. That's not hyperboloid. If it's elliptic a one sheet, then you have ellipses there. In fact, even with 2 sheets, your horizontal traces are always ellipses. It's only your vertical traces are hyperbolas. So that is a false, not a conditional false, a false. Okay. This is 12.6, false. Yeah. Number 3. Which quadric surfaces have both hyperbolas and parabolas as traces? That's almost a dead giveaway. Have both hyperbolas and parabolas as traces. The what? The hyperbolic paraboloid. Yeah. Hyperbolas and parabolas. Yeah. This one wouldn't. That's a paraboloid, but that has ellipses. That's why they call it elliptic paraboloid. So that would be hyperbolic paraboloid. Okay, I just want to make sure they get them right in the back. Hyperbolic paraboloid, sure enough. Okay. Number 3. Is there any quadric surface whose traces are all parabolas?
All parabolas?
Yeah. No, I don't think it could be. And that's a no. Okay, number 5. A surface is called bounded if there exists some capital letter M greater than 0 such that every point on the surface lies at a distance of at most M units from the origin. Which of the quadric surfaces are bounded?
I'm sorry to say that.
Okay. A surface is called bounded if there exists some capital letter M greater than 0 such that every point on the surface lies at a distance of at most M from the origin. Which of the quadric surfaces are bounded?
Hyperboloid.
Okay. Hyperboloid of two sheets, is that what you're saying, this one? Hey, look at that. It keeps going infinitely in z direction. Right?
Yeah.
The cone goes infinitely in the z direction. It's up and in. Paraboloid goes infinitely in the positive z direction.
So is it just a ellipsoid?
Ellipsoid is the only one that's bounded because you can set it whatever is the greatest number, A, B, or C, that can be your M. No point on there is going to be greater than that M.
So it's just
From the origin.
So just the ellipsoid is bounded?
It's bounded because, look at it, it's a self-contained. The others go infinitely up, except this one goes infinitely on Y and infinitely on Z and infinitely on X. So that one goes infinitely everywhere, and the cones go infinitely on Z. Or whatever the axis is. Okay? That one has a major and minor axis, nothing exceeds that at all. In fact, major, minor, and intermediate sort of. Okay. But yeah, the others, if you have an axis that goes infinite, it's not backward. Okay, so that better be ellipsoid, and it is. Number 6. What is the definition of a parabolic cylinder?
That is not enclosed or something? I don't know.
Okay. Draw a parabola in any plane you want to. XY plane, XZ plane, YZ plane. Draw a parabola in it. Then extend it in the infinitely if it's in the XY plane in the Z direction. If it's the YZ plane in the X direction. If it's in the XZ plane in the Y direction. That would be it. It's a parabola extended infinitely along the undefined thing. All vertical lines passing through a parabola. That's actually the better way to say it. Draw a parabola on any plane and then draw vertical lines to that plane through it. Infinite vertical lines. Okay. All right, homework exercises. Do any of the odds 1 through 5, any of the odds 7 through 11, any of the odds 13 through 19, 21 or 23, or both if you choose, any of the odds 25 to 37, and then any of the odds 39 to 45. Okay. Say again? That's chapter 12. It's 12.6. Okay. All right. Now, 12.7 is cylindrical and spherical coordinates. If you need this, look at it, okay? We're already sort of behind. Not only do we have to start a little late because we had to catch up stuff we didn't get covered this summer, but then we lost 2 Mondays in a row. So we're not going to go over 12.7. I can't remember if I have any YouTube videos of 12.7 or not. You can look and see. If you so, you can look at those too. But let's move on from here and go to chapter 13. So 12.6, you will have a question or two on your next test on 12.6, but that's all from 12. Yuck, that was not the right thing to do. But it's not too long. I've just got a few more clicks to get it back.
And what is 12.6?
When what?
I said, what is the title? And what is 12.6?
12.6 is quadric surfaces.
Oh, okay.
Was that in your book? Did you have a section? Yeah.
Yeah, I have that section. Just
Yeah. Okay. Okay, 13. This is the part that's always slow, PowerPoint. Here we go. Starting, operating, processing. All right, good deal. Not as slow as it was this morning. All right, they love these little things at the beginning. Now, the figure shown here is slightly different from the figure at the beginning of your chapter, but I think that the caption is identical. Okay, so I'll blow this up, and again, it's something that you don't have to know the caption or anything else about it. I'm tempted to say we're not going to do anything with this. It's just an example of, this is DNA polymers from helical curves whose spatial orientation influence their biochemical properties. Same thing that yours says. A lot of blah, blah, blah. Okay. And there is a whole branch of science, and I think engineering too, called polymer science or materials engineering, that deals mostly with polymers. They may have other things too, but it's a whole fairly new field of study now that we've gotten into polymers and stuff. But these are curves whose spatial orientation, how they're oriented in space, influences the biochemical properties. And what that would mean, if they're more tightly twisted or loosely twisted, or they're bending or doing something else like that, it may change things. Well, how in the world do we describe something in space like that? Well, how we do it is with something we call vector-valued functions. Okay? Now, here is an example of a vector-valued function. Okay? First is a vector. You tell that by the bold R. Generally, that's used for a displacement vector as a function of some independent variable t. And usually, your independent variables are scalars, not vectors. That would really be bizarre. Well, if it's a three-dimensional vector, then it has an x component, a y component, and a z component, and there's nothing that would restrict you from having each of those components being a function of that same variable t. Okay? Now, these are scalar functions here. This is a vector function here, denoted by the bold letter here, but each of the components is a scalar function of that same variable t. And you express that r of t as x of t comma y of t. That means that's the x component, y component, z component, but each of those are dependent on that variable t. Another way to write this I call angle bracket notation, also called component notation. But that's component notation. But that's component notation with the unit vectors. X of ti plus y of tj plus z of tk. Back when I was growing up, that was what we called standard notation or component notation, because you associate each component with its unit vector. But nowadays they use the angle brackets as a simple way to type it and express it, and it says exactly the same thing. Okay? Now, what happens to that r, that vector, as t changes? Well, this is an example of that. let's say we started at T0 somewhere back here. We don't show it. It could have been here or somewhere on back there. And then it's at T1. Now, there's a real tendency, especially if you've taken physics, to think of little t as being time. It may be, but it doesn't have to be. It's just some independent parametric value. Okay? At T1, this vector was here. At T2, it's here. At T3, it's there. R of t in general is some x of t, y of t, z of t. Okay? A couple of things to note here. Couldn't really tell what was happening here because this is a function in 3 dimensions. So this could be somewhere along x. That y could be actually negative or positive. It's hard to tell. Z certainly looks like it has to be positive. Looks like x has to be positive, but you can't tell on a 2-dimensional board where that's heading. Is it going into the board or coming out of the board? Now you know it's this side of the z-axis the way they have that drawn there. Okay? So it looks like to me it's starting somewhere around here and coming and doing this number, but again, it's hard to see what's happening here. A key here, this is some function. For any value t, there's only one value r. Now that value r has 3 dimensions on the 3-dimensional graph, but it's only one value for r. And r of t is here. Now if r of t is down here sometime, and even if r of t goes over here, and at t sub 17 is back here and happens to cross at the same point, guess what? That's a different t value from the t value here. Okay? So there's still only one thing. So this could be a curve that backs up on itself. In other words, vertical line tests make no sense in these kinds of curves. This is a function. It doesn't lose its function nature just because it looks like here there may be 2 vertical lines. A vertical line where it crosses more than once. That's immaterial now. The key is for any value t, you only have one r. Okay? Only one r. You could have more than one r, let's see, more than one t's producing the same r, but for any one t, there's only one r. Okay. That's your function. Now, that value t, the variable t, is called a parameter. Okay? There's no real reason to call it a parameter, except it's in 3 dimensions or more than 1 dimension, so we usually call it a parameter. Okay? Here we would just think of it as a variable in any one of those forms. But here we think of it as a parameter. It is the same. I mean, not making a big deal about it. The x of t, y of t, and z of t are the components, are the coordinate functions of that vector value function. Okay. So let's look at a few vector value functions that we could actually know. Okay. Here's R. Whoops. Wrong notation. R of t, because I can't write bold, I put the arrow over it, is this vector function t squared e to the t 4 minus 7t. Okay? Now, what would you say the domain of that function would be? What would be the domain of that function, R of t? Absolutely, all real numbers whatsoever. Why? Because it doesn't matter what the x value is, the y value is, or the z value is. It doesn't really matter there. It's what values the t can take on. That's your independent variables. Okay? T for t squared can be any number in the world. T for e to the t can be any number in the world. E for a linear function can be any value in the world. So yeah, for each one of those. Now if one of these had, if this had been the square root of 4 minus 7t, that would limit, the 4 minus 7t would have to be greater than or equal to 0. Then you figure out what t would have to be. If it had to be that there, it has to be that here too. So yeah, if any one of those has a limitation, a t in the denominator, a t in the square root, or a t in a logarithmic form, then you have to limit the values of t to be whatever that would require. If you have more than one of them, the intersection of all those functions. Okay? So here's another one. R of S. Now they've chosen a different name for the independent variable. Doesn't matter. This vector function would be the square root of S, e to the s, and s to the minus 1. Okay? What's the domain of that function?
I guess from 0 to infinity.
Okay? I sort of like the answer, except I don't understand the 0 part. Does that count 0 or doesn't count 0?
Definitely.
Why not? The third component, s to the minus 1, s cannot be 0.
Yeah,
okay, so it's anything greater than 0 to positive infinity. So if you had a parentheses from 0 to positive infinity, that's true. Bracket, no. Okay. Yeah, it has to be greater than 0 because this has to be greater than or equal to 0. That can be anything. This can't be 0, so therefore you make the intersection of all those greater than 0. That would be any s greater than 0. Very good. Now, usually they say this. Because I don't know why they bold the R, except that bolded capital R means the real number. I thought sort of a script-looking capital R meant real number, but they use a bold capital R. Okay. Now, we refer to that R of t either as a path or a vector parameterization of the path. So this R of t, and you can define where your t starts and ends, okay? And then that, the path traced by those values t, either the path itself or the vector parameterization of that path, both of those are names that we call R of t. Either a path or the vector parameterization of the path. And I have a hard time saying parameterization. I want to say parameterization, but it's not got that second E in it. It's parameterization. Okay. Now, back early in chapter 12, we described lines in R3 as using the vector parameterization. I don't know if you remember this or not, but R of t is equal to some point that's on the line. I can't write. Goodness gracious, I've been like this all day. X sub 0, Y sub 0, Z sub 0. Some point out there, and then the line goes through that point at some multiple of r times a vector, t times a vector r, okay? I'm sorry, vector v. Sorry about that, I can't read. All right, now, Where did they come up with the V? Well, this, what that means when you look at this means it's the curve R, the path R, the vector parameterization of R that's parallel to the vector V going through the point x0, y0, z0. Okay? So this is a point. That's what the sub-zeros stand for. And t is your parameter here, and v is just some vector that you want this curve to follow that direction. Then this will be a function for a line in 3 space. All right. Now, that wasn't the only way we expressed it. We also said, what if this vector v is this vector a, b, c? Okay, that just gives it some dimensions. That vector a, vector v, component a, component b, component c, in the x, y, z directions corresponding. Okay, now this is going to be a line. Okay, so this would then be, another way to express it is the vector x0 plus ta, or at, comma, y0 plus bt, comma, z0 plus ct. Oh, I said t and wrote 2. Goodness. I'm going very, very dry. Okay, now they wrote the t in front. It doesn't matter which way you write it. I usually write the variable second and the constant first. It doesn't really matter. They put ta, tb, and tc. Okay, here's the key. This is a line if for your parameter t, each component is linear. In other words, maximum exponent of that would be 1. Okay, no sines, no exponentials, no logs, nothing else, just a constant time zone. Okay, that then makes that line. Okay. No square roots, no squared powers, no anything other than x1 equal 1. Okay. Now this is something I don't think they do very clearly, and that's why I'm going to read you this. This is a line out of the, if you got your book, it's on page 690. I don't know if you'll find this in your book if you don't have this book. It is important to distinguish between the path parameterized by R of t and the underlying curve traced by R of t. The curve C is a set of all points x of t, y of t, z of t. Goodness, my head's hurting. The curve C is a set of all points x of t, y of t, and c of t as t ranges over the domain of R of t. The path in a particular way is a particular way of traversing the curve. It may traverse the curve several times, relative one time, or move back and forth, whatever it wants to do. Okay. I was trying to think of some sort of bizarre little examples you could give of that, but none of them. They're too far-fetched. All right, let's look at another figure. I think we're out of time, aren't we? Don't we go until 1:55?
Yeah.
Okay, sorry we ran out. So we'll pick up next time on example 1. Okay, and that's what that curve right there is. Let's see if we got enough, probably not for you to do many homework exercises. I think you do. You can do number 1, 3. I think you can do 5. Okay. So we'll hold off there. 1, 3, and 5. And the ones that we did from the previous section, 12 sections. All right, good deal. Goodness gracious. I'm almost getting dizzy. Don't know why. All right. And we will end it there. I've got 5 minutes before my